since 2021. I am the primary maintainer of the Stan compiler, but I've also worked on a bunch of other things. And I have what I think is kind of a fun talk. I'm going to be talking about how I think about Stan, how the compiler thinks about what a Stan model really is, and then we're going to see how, if you understand a bit about how Stan works, how that can help you when you're working in a different domain or an area where Stan can't be used directly. So the first part of this talk is understanding Stan. And I'm going to start with this claim that Stan is an entire programming language that is dedicated to just calculating one single number. This is not actually my claim. This is what my undergrad advisor said to me when he was pitching a project about Stan. I was a computer science major, so I came to Stan from a purely sort of programming language theory angle. And this claim did kind of grab me. I was like, that's kind of weird, a programming language that just calculates one number. What could that possibly mean? So I said yes to the project, and he sent me some materials to start to familiarize myself with Stan. And one of them was Andrew Gelman's golf case study, which I imagine a lot of you have probably read. And I read it. I thought it was quite cool. But I also thought he had lied to me, because there are two numbers here. Like, surely there's a second number that this case study is calculating. And if you keep going through the case study, they calculate a third number. And then I looked at another Stan model that had a matrix with 100 or 1,000 numbers that it was calculating in it. And so I, to be completely honest, spent probably the first 6 months or a year where I was familiar with Stan just being completely unclear what he had meant by this claim. It actually wasn't directly relevant to my research at the time. Like I said, I was treating it just as a programming language. And so it wasn't until later, when I started learning a bit more about how Stan worked under the hood, that I realized he was actually correct. And if you've ever written a Stan model where you've used this target plus equals form of a distribution rather than writing the sort of, y tilde normal sort of thing, you've actually seen the name of this one number that Stan is calculating. We call it the target. If you look at some older materials, we sometimes call it LP, short for log probability. But if you know a little bit about how MCMC works, you will have recognized this. This is this pi of q distribution in this Metropolis-Hastings acceptance ratio. And it turns out that there's a very cool thing that happens here, which is that to sample a model, fundamentally what you need to do is be able to take a set of parameters and just ask, what is the likelihood of these parameters under this model? And that one number is enough to sample. And so there's two cool things about that. One is that it's true, there is just one number being calculated. And the other thing is that these two numbers here are not actually outputs of the Stan model. They are definitely outputs of a Stan workflow, right? These are the things you're interested in as a practitioner. But from the perspective of the model, they're actually the Q that goes into the pi of Q there. They're the inputs to the model. So that's kind of the first cool thing that happens when you start digging under the hood of how Stan works, is you realize that there's this input-output inversion that is kind of the job of these algorithms. There is an asterisk on John being correct, which is that in practice, in most modern MCMC algorithms, you can't just get away with just the log density. You need some additional gradient information. And so you need this pi of q, but you also need some derivatives of the log density that will get you additional information for more modern samplers to be able to explore the space more efficiently. So it's technically true that you can just get away with the one number, but as always, the more information you give us, the further we can go. So that's the sort of basic introduction. And like I said, these parameters are the input to a function. And if you've ever actually looked at the output of the Stan compiler, you might notice that it's in C++. And so I have here a skeleton of a Stan model and all of the things that it generates. It generates a big C++ class. But before you all finish reading this, I'm going to say I'm not talking much about object-oriented programming today, so I'm just going to cut down to the bit we actually care about, which is just kind of this one function. The rest of it's just there for sort of niceties and other useful things like giving names to your outputs, which we can ignore for now. And so you have your parameters block, which actually ends up defining what the inputs to this function are. And then the model block defines the body of this log probability function. We call it log prob. It really does calculate one single number called target. And then it also uses a system called automatic differentiation, which is very cool. Hopefully you've all heard that before. If you aren't, I encourage you to look it up. It's like a very interesting thing I don't have time to cover in detail. but to calculate the derivatives. And so to make this more concrete, here is an actual Stan model implementing a linear regression, and then a hand cleaned up version of something like what the Stan compiler would actually generate. So does my cursor, is this visible enough if I use it to point for things? Great. So the first thing that happens in this log probability is we have to do some sort of data munging to get the parameters you wrote in the parameters block back into the names that you want them to have. So there's some stuff that we read in an alpha, just a scalar. We read in beta, which is a vector of length p, so you can actually just kind of read that off directly from the Stan model. And then sigma has something more interesting happen. We have this lower bound, and so there's some functions that are in the C++ library that Stan is built on top of that handle this turning a variable that has support over the entire real number line into a positive variable. And if you've taken a multivariable calculus class, you probably know that that kind of thing doesn't come for free, and so there's also some adjustment terms that need to be added, and that's all handled by these lines here. And then the rest of this code is, I would argue, more just a line-for-line translation of the Stan model. In fact, if I had written this as target plus equals normal LPDF alpha bar 0, 5, then it would look basically, if you squint, more or less the same. We have some accumulator where we're adding in these terms, just doing a summation, and the terms are densities for your priors, and then the density for your likelihood term, which, you know, we've rewritten some of the linear algebra and stuff like that to call into our library that handles the autodiff, but otherwise it's like the exact same operations. And this does just return one number, although that number is this StanMath var type, which is the internal name for our autodiff type. So it also has a system outside of this that then can turn that var type into not just the value it's calculating, but also derivative information. And so this sort of gives, there's an interesting connection to the talk if you were here for the keynote this morning. Stan is kind of a different PPL from some others in the sense that it really is just organized around writing these C++ log density functions. They are the kind of thing that you can write yourself if you are really crazy. And obviously C++ is very fast, it provides a lot of efficiency gains, but it's also kind of hard to write. Like, I've been writing it for years and I still don't trust myself the first time that I write something in C++. And so Stan is designed to kind of give you a nice user interface for writing these models and then has a bunch of support around that. The other thing is that autodiff is nowadays kind of a common technology, but it was less so in the early 2010s, or the early 2010s when Stan was first being developed. And so the C++ math library that we have in Stan is kind of our own thing that we built for this purpose, and so we wanted to be able to target it very directly from the Stan language. So you are now all experts in the Stan compiler, and I'm looking forward to your contributions. But I want to now talk about, if you think about models in this way as really just writing down log density functions, it opens up some other interesting opportunities. So I'm going to talk a little bit specifically about the JAX package. So like I just said, Stan is, from a 30,000-foot view, a domain-specific language for writing down a C++ function. That's really all it does. And it has this nice feature that those output functions are automatically differentiable. JAX is positioned in a different way. It's a library in Python that does a lot of general purpose scientific computing and mathematics tasks. But it has one thing that's in common that ends up being sort of the unifying thing, is that it also is automatically differentiable, but it also provides a lot of other things. So when you write code in JAX, not only is it automatically differentiable, but it also provides just-in-time compilation, the ability to compile it and ship it off to a GPU, the ability to work over batches of data to automatically parallelize your code, and do a lot of other very cool program transformations. And those program transformations mean that JAX is very hot right now. If you follow the MCMC algorithm development literature, you may have noticed that there are lots of algorithms out there that are, the papers will actually specifically mention JAX as the reason or the target that they are targeting, of like how they're trying to leverage newer hardware. And then there are other situations where the paper might not mention it, but if you click on through to their code and you read the code, you'll notice it's using JAX. So yesterday's talk on Riemannian HMC, if anyone else followed the link at the end of the slides, you may have noticed that that code also used JAX. There's one problem, this is StanCon, and if we want to use these algorithms, we can't use Stan. you have to have a log density written in JAX in order to use an algorithm that assumes that it can use all these JAX tools on your log density. So recall this is the same slide from a few minutes ago. And I'm going to say that this does not have to immediately be a cause for despair, because we know how Stan works. We have Stan models. We can look at what we generate in C++. And if you want to, you could do what I'm doing on this next slide and just hand translate it into JAX's language. And there is really a sort of direct correspondence. So JAX and Python provide some nice things. I don't have to worry about alpha and beta. Those just kind of come for free. But I still do have to do something for this sigma parameter that I want to have a lower bound. Unfortunately, we don't have this nice read-constrained lower bound function in Stan, so I had to go into the reference manual and read what's actually happening mathematically and re-implement that myself. And then I have to do this target accumulation of the prior and the likelihood like in Stan. But I have this sort of unfortunate thing where instead of saying exponential, I have to say jnp.sum stats.expon.log PDF. But if I'm kind of willing to ignore that mouthful, I would say that this isn't that bad. Of course, for the same reasons why we probably don't want to write the C++ directly, we don't want to write the JAX directly, and that's sort of where we're going to go from here. And I want to specifically focus in on this jnp.exp. Obviously, the lower bound is not that bad, but there are other things in Stan that are extremely useful, like Cholesky factors, and I really don't want to look up the math for those. And so I probably was underselling Stan a few slides ago when I was just highlighting the fact that it was producing one number and using autodiff, because it also has this extremely useful feature. I mean, we've been seeing so many models the past few days that have had constrained parameters, both for efficiency and for modeling reasons. And so the fact that the inputs to this function can have these very bespoke mathematical constraints is another reason why Stan is like a very powerful domain-specific language. And so, there's this extra bullet point that I probably could have had if I was a more honest presenter that says that Stan has constraints. But of course, JAX has more or less anything that you can write in Python. You can kind of mix and match these library components as you please. And so we've started writing a library. I think when I proposed this talk, I think we thought that we were going to be further along, and then we started working on walnuts. So that's how these things go. But I can now put, the JAX panel here is exactly the same code as a couple slides ago. And then this is using a library that we're tentatively calling density JAX. And there's really nothing magic in there. I promise we did not invent a new language. Like, it's all just simple Python functions. Things like this exponential function really just are jnp.stats or jnp.sum stats.expon.log PD. There's nothing magic in there. But the thing that we realized is that the part that's missing from JAX, we have the autodiff, we can write the densities, but the thing that was missing was just like a way to do these constrained parameters in a way that feels at home for Stan users. And so we have this declarative way of listing out your parameters where you can say alphas are real, betas are real with a size, meaning like a vector, or in JAX and NumPy world an array. And then sigma has this positive thing. And then you'll notice that the density function, besides just having nicer and shorter names like exponential, it also is now, it doesn't have to worry about sigma. Sigma just comes in, and like in Stan, you can just assume it's a positive number. You don't have to worry about anything yourself. And then keeping the density JAX in the same place, flipping over, this is the original Stan model, and this is sort of our recommended style guide using these little helpers. If you have a problem where you need to write JAX, and you have these helpers at your disposal, I think you can kind of make them look the same. Like, I think if you squint, these don't feel like totally different worlds to each other anymore, like they might have when I was showing you the raw JAX and the raw C++. And that's sort of sorry, I saw someone want to take a picture of this, so I'm just going to go back for 1 second. But my message is really that there is no magic in software. If you've never looked before at how Stan works, I think that it's worth doing. I think that it's a useful thing to kind of know how your tools work. There's also no magic in density JAX. It's just a couple small Python functions that I think most proficient Python programmers who read a bit of the JAX doc could probably write themselves. And I think this is also a very cool time to be interested in statistical software, because if you think back to when Stan was first being built, there weren't really autodiff systems off the shelf that would work for something like Stan, and so they had to build one, and that means that now, 10 years later, we have 100,000 lines of C++ code that we have the honor and pleasure of maintaining, but also the pain of maintaining. And now you can kind of pull these off-the-shelf parts. JAX has a wonderful autodiff library. There's tons of special function support. And you get to use it in kind of this embedded way. And so I think that it's always worth knowing a little bit about how your tools work, because it also means that when you are in a situation where your tools are taken away, you can still kind of think critically about what you really need to build. We didn't need to build an entirely new language targeting JAX. We just needed to build some library components that kind of make it feel more at home. And so with that, I'll say thank you. There's a paper. This repo hasn't been updated in a couple months. Like I said, we've been busy, but we're hoping to write this up as a paper and a package that will eventually kind of just contain these utilities and make it easier if you want to try out these new JAX-based samplers, but you kind of you have a Stan dialect to how you think about modeling.
Thank you very much. It's a super interesting talk. Open the floor to questions. Anybody have any questions? We'll start wherever you want. Furthest away, maybe? Good thing you can throw this mic. Here we go. Nice.
Thanks. So I feel like the obvious question would be, is like a Stan to density JAX transpiler on the arc of all of this?
Yeah, so this is the things you don't tell people in a sales pitch, which is that there are some Stan models that probably cannot be directly expressed in JAX. For example, JAX does not like while loops, and which would make it quite difficult for an automated translation. Now, you as a modeler might have some while loop because you're calculating some iterative process, and you might observe, I write this while loop because in theory it's infinite, but in practice it always converges after 50 iterations. So I'll just write a for loop that takes 70 iterations, and that'll probably be good. And that is a decision that you are totally empowered to make, but I think you would be really ticked off if an automated tool made for you. And so there are definitely some things that can't be translated automatically. But I have had people ask me about this in the past, and I often say, I saw Paul was nodding at the same question. There are subsets of the Stan language that you certainly could translate automatically, and I think the things that are generated by BRMS probably often fall into those subsets, and so I think that that is a potential area for research. We could also talk about ideas of trying to detect if you're doing something JAX doesn't like and then having an extra set of errors or something, but I think that's a bigger project, but it's definitely something that, like I said, I like Stan, I like compilers, I'm definitely interested in that, but we don't have an immediate plan, no.
Cool.
Yeah, we're going far left now, I think.
I feel like I should have stood over here. I feel like this half of the room has been neglected, broadly speaking.
I think throw it across and get someone to pass it, yeah.
Yeah, thanks for the great talk. I will ask maybe the orthogonal obvious question, which is, there's CMD StanPy and PyStan and these Python tools, and you can hook up external Python code to JAX in theory. I've tried doing this with StanPy before, CMD StanPy before. It doesn't work very well because of latency issues and stuff. So why invest so much into a new software tool now that you're going to probably have to maintain, as opposed to try to enhance the current tooling of the Stan ecosystem? For example, for people who have these giant Stan models that they don't want to re-implement in posterior DB or something like that.
Yeah, I think that's certainly a fair question. Part of the reason this project started is because we wanted to try out these new samplers, and so we were willing to write new models to do it. But I think that there also are interesting ideas. So I will say if you are using JAX on the CPU, which is not generally how they recommend doing it, there actually is a way to connect BridgeStan to JAX, and this is something that we did a few years ago with Justin Domke, who was doing some research on variational inference algorithms that were implemented in JAX. And it does work, but as you say, there's this overhead. And as for GPU support, which I think is a lot of the reason why people are drawn to JAX as accelerators, Stan just lacks a lot of GPU support, and part of it is for those same reasons. GPUs also don't like while loops. A lot of those decisions made in JAX were made to make GPUs easier for JAX to generate stuff for that wasn't really being considered for Stan at the time. And so we would definitely need a lot more GPU support. There would also probably be some issues with JAX is largely CUDA based, and we use the more open OpenCL standard, but getting everything to talk to each other there would probably have some difficulties. And so it's not that we're not interested in that, but I mean, the full, if I actually showed you the import of those full things, that's like that entire slide of density JAX is like maybe 200 lines of code. It's really, I also am nervous about maintaining new things, but this is really not that much, and I don't expect it to change that much over time once we have some of those, some more of those constraints implemented in Python. But yeah, I don't know if that got at your question.
It got at my question. I'd love to talk to you after this.
Oh, for sure.
If you don't mind handing the mic diagonally backwards, I think there was a question a couple of rows back. Bit of teamwork here. Thank you, guys.
It's like a bucket brigade.
Thanks very much. I think my question's sort of been answered, actually, in the previous answer. But I was sort of wondering, what does this give us that, for example, TensorFlow probability, with their collection of distributions and default bijectors and stuff, wouldn't? Is it just the Stan compatibility, or is there something a bit more subtle under the hood?
The main idea is just the sort of familiar approach to writing models. So TensorFlow probability does give you ways of doing like constrained transforms, for example, but it ends up looking like the generated C++, where there's some special function you call that will turn an unconstrained sigma into a sigma that's positive. And so I think when we got excited about this idea was when we realized we could do something that looks more declarative like Stan, where you, rather than writing some code that turns sigma from a real number into a positive number, you just write sigma : positive, and that like imbues that meaning into your code for you. But no, and in practice, like, I believe if you dig through like the code of what's actually happening when you write stats.exponential, I think that they end up at the same place as some of the TensorFlow distributions. And it's entirely possible that like a lot of this ends up just being wrapper calls that kind of give you a more familiar user interface. And like there are some differences in the approach, but we're not currently planning on like rewriting the exponential distribution in JAX or anything like that. We're just going to use those parts when they're available.
Amazing. I know there's a couple more questions in the room, but just to stick to time and make sure everyone can get some lunch today, we're going to say thanks again once to Brian, and then we'll move on to the next speaker.